Okay, so welcome to Math383 Complex Analysis. So this is lecture 7, and what I want to do today is go into excruciating detail on evaluating integrals. So no more hand waving, no more go home, bang your head on this for a while. I want to put in all of the steps and show you how do you actually do stuff like this. Okay, so we will be looking at consequences of Cauchy's theorem, basically the residue theorem. Later in the semester, it explicitly extracts this as a theorem. We might explicitly extract that as a theorem today. I will try to look at examples related to the following three: 1 minus cosine x over x squared, sine squared x over x squared, and 1 over 1 plus x squared. All of these functions are nice, except at potentially finitely many bad points. Some of them might be nice everywhere, but they might have only they can only have finitely many bad points. It's a wonderful theory to try to ask yourself, well, what would happen if they were bad infinitely often? We are not going to deal with that right now. If you want more examples of stuff like this done explicitly, I've posted this on the webpage under additional videos. I'm also just putting the link in here as well. All right. So we have a bunch of different integrals to do. I am going to start with one of my favorites. Of all of them, I think it's the easiest. And so it's going to be, so f of x is 1 over pi 1 over 1 plus x squared, or just 1 over 1 plus x squared. The pi is not that big of a deal. Does anybody remember this function from probability or statistics? It's related to the arctan. It's the Cauchy distribution. So Cauchy gets credit today, not just for his theorem in complex analysis, but for his distribution. It's a great day for Cauchy. So this is one of my absolute favorite probability distributions. So something is a probability distribution if it's non-negative and if it integrates to 1. So the 1 over pi is to help us show that it does integrate to 1. Now, imagine you are divinely inspired and you decide, I've always wondered what is the tangent of the arctangent of x. Anybody tell me what the tangent of the arctangent of x is? X, right? I'm taking, this is an English proof. I'm taking the tangent of a number whose tangent is x. Oh, okay, I get back x. So now let's take derivatives. So this is going to be tangent prime at arctangent of x times arctangent prime of x, and the derivative of x is just 1. So arctangent prime of x is 1 over tangent prime at arctangent of x. This is, of course, a more general result is lurking in the background. If I know f of g of x is x, if f and g are inverse functions, I can get g prime if I know f prime. So the derivative of arctangent is 1 over tangent prime at arctangent of x. Well, we can do a little bit better. So let's draw a triangle, and I want my angle down here to be the angle arctangent of x. Can anybody tell me, there's infinitely many correct answers. Can anybody tell me good side lengths so that the tangent of this angle will be x?
Opposite side is x.
Good.
Side is 1.
Good. Yep. So does anybody remember what's the derivative of tangent? Secant squared. If you don't remember the derivative of tangent is secant squared, what can you do? Thank you for saying sine over cosine in the quotient rule and not saying Google, right? But yeah, Google Mathematica would also give that to you, but you can just use the quotient rule. All right, so this is now the same as, all right, so you said the derivative of tangent is secant squared. If there was any justice in the world, secant would go with sine and cosecant would go with cosine, but there isn't. Secant is 1 over cosine. So if the derivative is secant squared and I have 1 over that, this is the same as cosine squared of arctangent of x. Okay, I now want the cosine squared of the angle whose tangent is x. Well, if I look at the triangle, that's just going to be 1 over the square root of 1 plus x squared. That's just 1 over 1 plus x squared. It's not wrong to say that the derivative of arctangent is 1 over tangent prime of arctangent or cosine squared of arctangent of x. Cosine squared of arctangent of x is a nightmare. 1 over 1 plus x squared is very pleasant. And so now if I use this, if I want to integrate switched. So if I now want to integrate from minus infinity to infinity of 1 over 1 plus x squared dx, this is the same as twice the integral from 0 to infinity, 1 over 1 plus x squared dx. This is going to just be 2 arctangent of x evaluated at 0 and infinity. So what angle has a tangent of infinity? Pi over 2. And what has a tangent of 0? 0. And there's our pi. So this proves that the normalization really should be 1 over pi to make this a probability distribution. Right? Is everybody comfortable with this proof to integrate from minus infinity to infinity of 1 over 1 plus x squared? This is the standard Calc 1 approach. You can actually use this to form formulas for pi. If there's time at the end of the day, I'll circle back and give you some formulas for pi from this. This, of course, is a class in complex analysis. So I'm going to show you how to do this using complex analysis. If all I can do is do this again, are you impressed? No, right? And if you're impressed, you're impressed easily. What if I could do this with a 4 over here? So can you come up with a function which is the antiderivative of 1 over 1 plus x to the 4th? Or 1 over 1 plus x to the 6th. I can show you I can handle all of those using complex analysis. So you can see that not only am I able to do what was done elementarily, but we can do a lot more at the same time. So let's consider now the function f of x is 1 over 1 plus x squared. And I'm going to go, the standard, here's minus r, here's r, and I'll come down like this, and then I'll come along my semicircle like this. And now I have to complexify this function. So can anybody think of a nice function that reduces to 1 over 1 plus x squared when my variable z is x? Yeah, 1 over 1 plus z squared, right? This is not mysterious. This is similar to the integral test from sequences in series, that I need to find a function that is equal to a sub n whenever x is n. Maybe I should just replace every n with an x. Oh, that works. So basically, your first thought should always be, let me replace every x with a z and study that. This is not necessarily the only choice that works, but it's not a bad first thing to try. Now, if I look at this function does not blow up whenever x is a real value, which is good. Where does this function blow up? Where is this function not holomorphic? At I, anything else? Negative I. So I can write this as this is 1 over z minus I, z plus I. And there's a lot of ways you can now try to understand what's going on. So clearly, there's going to be two troublesome points. There's going to be the troublesome point here at I, and the troublesome point here at minus I. Which one concerns you more? Got a 50-50 chance. I. Why I? It's in the region. So it's the one that at I that's going to matter. So there's a couple things we could do. I can write this. Does this look familiar at all? If I put a minus sign over here, the z's will cancel. If I put a 1 over here, I'd get z plus I minus z minus I. So I'd get, I think, a 2i. So I want a 1 over 2i, I think. What technique is this? Partial fractions, right? Whenever you ask people, what is your least favorite technique from integration? The answer is partial fractions, unless it was so traumatic that they forget that they saw partial fractions, and then when you remind them, say, I'd like to change my answer, please. Right? So I just did a partial fraction analysis. Partial fractions are actually good for things. Right? There was a reason we taught it to you. It's not just because your teacher was sadistic. That's completely independent. This can be used for good things. If I want to try to figure out what's going on, one of these functions is extremely well behaved near I. One of these functions is not. And so near I can expand just one of them. I can write this as, I can factor out the 1 over 2i, and then the first one, it's 1 over z minus I. So how can I deal with that? I'm sorry? So yes, so what I'm going to do is I'm going to be coming down here, and I'm going to come up, go around, and come back and continue. And so I will go around I counterclockwise. And so I really care about what's going on near I. So I want to expand 1 over z minus I as a power series in z minus I. And I want to expand 1 over z plus I. Yes. It doesn't have to, because I just take the limit as they get closer and closer and closer. And so my feeling is, why give myself even an additional limit to take? Why don't I just go back down the way I came and just make it much easier? Technically, then you've got a curve where you're heading this wall twice. So it's sometimes nicer to just say, let's separate it a little bit and take the limit. I'm not going to bother. No. So we'll figure this out later. But we'll have two pieces here. We'll have 1 over z minus I and 1 over z plus I. And again, I want to just show multiple ways of doing this problem. Okay. And so what we would get is the integral from minus r to r of f of x dx plus the integral over the semicircle of radius r of f of x, f of z dz plus the integral over the circle centered at I, and I'll write here with a negative orientation because I'm going clockwise rather than counterclockwise, of f of z dz. And what will that equal? 0. And if I look at the three pieces, the first piece, as r goes to infinity, is exactly what I want. That's just going to be the integral along the real line. The second piece, the integral over the semicircle, I'm going to show that goes to 0. And then the third piece, what do you think the third piece is going to go to? No.
Minus pi.
Minus pi, because we know that the answer has to be pi. So it's got to go to minus pi. It's nice that we know what the answer is, so we can just be watching the algebra and see, where does your professor make a mistake? All right, so you know the punchline that's coming. So let's first look at the integral over the semicircle of radius r of 1 over 1 plus z squared dz. And so, it's this piece over here going from minus r to r. So can somebody tell me what is the largest this can be on the semicircle of radius r? Why 1 over r squared? You're essentially correct, you're morally correct, but you're wrong.
Let's do like 1/2 1 over r squared.
Well, but one half, that might be too small.
Well, I mean, times 2. That's 2.
So you mean 2 over r squared?
Yeah.
2 over r squared is probably safe.
I think it blows up.
Well, we're staying far away from the point where it blows up.
Oh, like just a contour.
Yeah, r is going to infinity. So r is large. If there wasn't the 1, what would you bound it by? If there wasn't that 1, if it was just 1 over z squared, what would you bound it by? 1 over r squared. And in fact, it would always be 1 over r squared if there was no plus 1. Because I'm on a circle of radius r centered at the origin. How far away am I from the origin? R. I'm always r. But now I have the plus 1. So when I'm adding numbers, if I want to make things large, the best is when they're in phase. If I want to make things small, what's the worst they could be? Opposite. So what would be the worst case for us for z squared and 1?
1 minus r.
Yeah, but not 1 minus r squared. Other way, r squared minus 1. So this would be at most 1 over r squared minus 1. So morally, yes, it's 1 over r squared. If you want to be safe, 2 over r squared. When you become a professional, complex analyst or number theorist and you stuff like this, you have to be careful about stuff like this. I'd much rather just put in a factor of 2 than worry about all stuff like this. So now the question. Okay. I'm sorry? Oh, okay. So if I now integrate over the semicircle of radius r of 1 over 1 plus z squared dz, that's going to be less than equal to 1 over r squared minus 1, largest value. And then what's the length of the curve? Pi r. So this is, pi r over r squared minus 1, and that just goes to 0. So this would be the rigorous way of showing that the contribution over the semicircle goes to 0 in the limit. All we have to do now is just integrate the function f of z over that semicircle centered at I. Notice how we've reduced integration to really nice shapes. So in this class, the shapes we shall consider: straight lines, semicircles, full circles, which is the union of two semicircles, stuff like that. We're not going to consider arbitrary lines. For the most part, everything we need is going to be something of this form. Okay, so now I want to integrate over the circle of radius epsilon of 1 over 1 plus z squared dz. I'm now going to have the circle oriented correctly because we just move it over to the other side. All right, so this is the same as integrating over the circle of radius epsilon. I have that factor of 1 over 2i, and I have 1 over z minus I minus 1 over z plus I dz. Okay? There's lots of ways we can do this. One way is I can pull out, first of all, the 1 over 2i. That's not a big deal. And then it's the integral over the circle of radius epsilon of 1 over z minus I dz minus the integral over the semicircle over the circle of radius epsilon of 1 over z plus I dz. And just to make sure that we're all on the same page, here's I, here is my circle oriented in the correct way, and down here is the real axis. I claim one of these integrals is very easy to do. I'm sorry? The second one. What's the second one? Why is it 0? So the function is holomorphic in region, has primitive. So the second one is really easy. The first one is essentially just integrating the function 1 over z. And so we can do a change of variables to make things a little bit clearer. So for this one, let's let z equal I plus zeta. So what would dz equal? D zeta. And so we would get the integral over a circle. Now where's its center? 0. So if you want to really be pedantic, I should not be writing c sub epsilon. I really should be writing c sub I of epsilon over here. And this should really be C sub 0 of epsilon over here. Right? I should be keeping track of where are the circles centered. And so I would then be integrating the function 1 over zeta d zeta. Oh, okay, that's what we've done before, except I'm now using zeta rather than z. Is it? It's 2 pi I. And so I'll keep the 1 over 2i that I had before. So I have 1 over 2i times 2 pi I, which equals pi. And that finishes the argument. Now, whenever you're doing something, you always want to make sure that you can reproduce it, that you could do something similar. Was I moderately clever at any point in setting things up? Yeah. This is a standard contour. There's 2 places where it blows up. But when we analyze 1 over 1 plus z squared, I used partial fractions. What if you didn't see partial fractions? Could you still solve the problem? Well, let's just try to think of what would happen if we hadn't seen partial fractions. So, avoiding partial fractions. So we have f of z is 1 over z minus I, z plus I. And again, I know that we can use partial fractions. I want to show you the general technique. I want to write this as a sum, n goes from minus n to infinity of an z minus I to the n. I want to expand it out. And then the reason is, then the integral over this semicircle centered at I of radius epsilon of f of z dz would be 2 pi I, the sum n goes from minus n to infinity. Well, I'll avoid the 2 pi I for now. Would just be the sum n goes from minus n to infinity, an, the integral over the semicircle of radius epsilon centered at I of z minus I to the n dz. Right? I'm basically just interchanging the sum and the integral. And we'll assume that we can justify all of this. I'm just trying to show you formally what we would be doing. And now, for those integrals, which is the only term that matters?
Negative first term.
Negative first term. So this would then just be a minus 1, the integral over ci epsilon of 1 over z minus I dz. And what is the integral of 1 over zi dz? That's just 2 pi I. So if we had the 1 over 2 pi I outside, we would have just gotten 1. This is just 2 pi I. So we just get 2 pi I times the negative first coefficient in the expanded Taylor series. That's sometimes called a Lorentz series. So the idea is we've reduced integration to finding the negative first term in the Taylor series expansion. I don't care about any other term in the Taylor series expansion. I just care what is the negative first term. And when I do my integral, that's the only thing that survives. So what we want to do is we want to Taylor expand 1 over z minus I, 1 over z plus I, and find the negative first term in the Taylor series expansion. So we need negative first term in Taylor series of 1 over z minus I, z plus I. Okay, one of those terms is ideally suited to find its power of z minus I. Which one do you think? Well, we've already got a z minus I there, right? So we have f of z is 1 over z minus I, and then we have 1 over z plus I. So we want to expand 1 over z plus I. And which term do we care about in the expansion of that? I'm sorry? When we expand 1 over z plus I, what term do we care about in its expansion about the point I? I'm sorry? Nope. We care about the -1 coefficient of everything. I've got a z minus I outside. That's already giving me a power of -1. Which term do you think is going to matter for the 1 over z plus I? Which term? Not the first degree term. The 0th term, the constant term. All I care about is the constant term. Can anybody figure out what the constant term is of 1 over z plus I? Nope. So only need constant term. Nope. At z equals I. 1 over 2i. Right? How do you get the constant term? You just evaluate the function. If I wanted the linear term, I would take the derivative. If I wanted the quadratic term, I would take 2 derivatives, and then I either multiply or divide by 2 factorial. Now, again, the goal today is to do everything in excruciating detail. So I'm going to show you how to expand 1 over z plus I. Again, I understand it is not needed for this problem. That is why I am doing this problem. I want a problem where we can constantly check and make sure we haven't done any algebraic mistakes. Okay. So the 2 big things we do in mathematics is nothing. What are the 2 ways to do nothing? Add 0. So what do you want to do here? Do you want to add 0 or do you want to multiply by 1? Multiply by 1? Why multiply by 1? It's not multiply by 1. You want to add 0. We want to expand things about I. So I don't want a z plus I. I want things like z minus I. How can I get a z minus I? So I need a z minus I. What could I add so that I would get a z minus I to z plus I? -2i. I can't add -2i. I'm not allowed to do that. I can only add 0. I could do -2i plus 2i, something better than -2i.
Consider a Taylor series at c plus I.
Right, that's what we're trying to do. So I want to have a term that looks like z minus I. Right, I'm saying for this particular problem, we know that we only need the constant term. We can just plug in z equals I and we get 1 over 2i. I agree. But I want to expand this in terms of z minus i's. How should I write 0 so I get a z minus I? I've got z. What should I put in next? I want to get z minus I, so put in, I'm sorry? I can't put in -2i. Can't put in plus 2i. I have to put in 0. How can I put in
2i plus 2i?
Okay, but I don't want to do -2i plus 2i that's no minus I. And now what do I put in after the minus I? I put in a plus I, right? I've added 0. And now I've got a z minus I. So this is the same as 1 over z minus I. And now what do I have? I've got 2i plus z minus I to the -1. Does this look like anything you've seen before? It looks like geometric. So geometric is 1 over 1 minus r is 1 plus r squared plus ... where r for us is going to be what? Almost. Almost. Yeah, so we've got that pesky 1 over 2i. So let's get rid of that first. 1 over z minus I. Then we're going to pull out a 1 over 2i. And then we'll have, I guess I'll go back to writing this. 1 minus, I'll do negative z minus I over 2i. Yes? Is that going to work now? I've tried to write it so it's as close as possible to the geometric series. And so now I would take I is going to be negative z minus I over 2I. So this would be 1 over 2I, 1 over z minus I. And now I would start to expand. I would get 1 plus, so it's negative, so it's actually going to become a minus, z minus I over 2I. And then the next one would be plus z minus I over 2I squared, dot, 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 dot. And if you look at it, you see a to the negative 1 is just 1 over 2I. And so we recover that again because I only care about the 1 over here. This term has a z minus I, which cancels with the z minus I here. The next term is a z minus I squared, so I'm going to have a z minus I. So this is how I can do the Taylor series for something like this. It's actually not that, yes.
Could you explain how we get that negative? I mean,
How we get which one?
the 80 negative 1.
Well, just when I start multiplying things out, here's the constant term here. I have a z minus I to the negative 1. So this is the n equals negative 1 in the Taylor series. Then the next term here is I have a z minus I times a z minus I in the denominator. Those are going to cancel, and that's going to give me a constant term. And the next one, I'm going to have a z minus I squared. I'll have a z minus I downstairs. It's going to give me a z minus I to the first. So when I expand this out, I get 1 over 2I times z minus I minus 1 over 2I squared. Then plus 1 over 2I cubed z minus I.
Yeah, okay.
And so that's where we get the Taylor series. And so this is another way to do this. And so now if I give you more interesting problems, you can try to think, do I want to use a technique like this? Are there other methods I can do to just figure out which term do I need? If I gave you a 1 over z minus I cubed, which term would I need when I expanded 1 over z plus I? So if I had 1 over z minus I cubed, what term would I need when I expanded 1 over z plus I? The squared term. And so we've actually got that over here, by expanding it like this, or you could also get it by just taking derivatives of 1 over z plus I. And so if you just took 2 derivatives of that and either multiply or divide by 2 factorial, it would work that way as well. So this is how you can do problems like this. So things to ponder. Do you think you could do this integral? 1 over 1 plus x squared to the n dx. N is a positive integer. Do you think this would be easy or hard? It's what we just did, right? You would still just take f of z is 1 over 1 plus z squared to the n. So it's going to be 1 over z minus I to the n, 1 over z plus I to the n. Yeah, and so I want to have the n minus first term from the second factor. So just need the n minus first term from the second factor. So now the partial fractions is not going to look as pleasant. Yes?
What if we tried to do 1 over 1 plus x?
So that was the next one. So the next one to ponder. Yes. I'm going to do 1 over 1 plus x to the 2n. Why am I doing x to the 2n and not just x to the n? It's worse than that. Yeah, well, if I took n to be an odd integer, if I did 1 over 1 plus x cubed, when x is negative 1, it blows up. So this, or I could do the integral from 0 to infinity of 1 over 1 plus x to the n dx. It turns out that we can't actually evaluate all of these. If I gave you a specific n for either one of the, for at least the first one, it's going to be extremely similar to what you've done before. As a nice exercise, try to do n equals 2. And you will see that complex analysis will allow you to do this. Now you start getting polynomials and you have to find roots of polynomials. These are actually very special polynomials. It's not so bad. Okay, any questions about this? I hope you can see the power of complex analysis. I can quickly pass to this. This one isn't so bad for finite n. Try doing this with calculus. Right? I will give extra credit, but I do not advise you to do that extra credit of trying to do these elementarily using calculus techniques. Okay. So completely explicit. So let's consider the integral from minus infinity to infinity of sine squared x over x squared dx, which after a change, so integrating by parts, is the sine of x over x dx. Integrate by parts. So I'll leave that as an exercise for you to do. We just have to evaluate this integral. There's a couple of ways we can do this. One approach is we could write sine of z is e to the iz minus e to the minus iz divided by 2i. So that's one way to write sine. Unfortunately, if I do that, one of them is growing in the upper half plane, and the other one is growing in the bottom half plane. So I can't do one thing and handle everything simultaneously. I'm going to have to break it up and say, I'm going to integrate this one, I'm going to integrate that one, that one. It can be done, but it's a little bit of a pain. The other thing we could do is we could say, the sine of x is the imaginary part of e to the ix. Because e to the ix is cosine x plus I sine x. So what if we study the integral from minus infinity to infinity of e to the ix over x dx and take imaginary part? Do you think this will work?
Does taking the imaginary part of the whole integral equals to taking just the integral of the imaginary part? Does that?
Well, this is also going to have a real part. I'm just saying, yeah, just throw away the real part.
It would be kind of interact in a weird way.
No, they're completely separate. I can write this as, I have my function. Here's the real part. Here's the imaginary part. Just integrate each part independently. What happens when you look at the real part? What would you be integrating? Cosine. Cosine is an even function divided by x, which is odd. Okay, we have an odd function, symmetric interval about 0. Its integral should be 0. That's great. The problem is cosine of x explodes, right, at 0. And that can be a little bit of a problem. So what we could do is we could do maybe something like this: minus r to epsilon, epsilon to r. And if we integrate our function over that, then we're in great shape, right? But we would have to add on that little extra bit. Okay. So let's try to see what we would get if we try to do the integration. And so here's minus r, here's minus epsilon, here's epsilon, here's r. And so a lot of it is going to be pretty straightforward. I'm going to come down like this. I'm going to come down like this. I'm going to come along like this. And my function is going to be f of z is e to the iz over z. Where is the only problem point for that function? Yes?
0.
0. Yep. So only pole is at 0. Okay. So do you want to include 0 in the region or not? Okay. So there's two ways to do that. So if you don't include 0, then we're going to have to do something like this. We're going to add this extra curve like this. And now the function is holomorphic in the region. So what's the integral of f along this whole curve? 0. So we get 0 is equal to the integral from minus r to minus epsilon of, I can write that as f of x dx, plus the integral from epsilon to r of f of x dx, plus the integral over the semicircle of radius r of f of x dx, plus the integral over the semicircle centered at 0 of radius epsilon in the wrong orientation, because we're doing it clockwise, f of x dx. Now, over here, as r goes to infinity, this goes to the integral from minus infinity to infinity of what? Well, so we'll have the cosine x plus I sine x over x. The cosine x over x, that's going to integrate to 0. So it's going to go to I times sine of x over x dx. So those two pieces in the limit is going to just give me I times sine of x over x. It's going to give us the imaginary part times an I. You have to be very careful and remember there's an I there. Everybody comfortable with this? Okay, now we have two other contours, two other curves we have to do. We have to do the semicircle, and then we have to do the other semicircle. Let's do the big semicircle first. So we have minus r to r. I don't care what's going on every place else. I got my big semicircle like this, and my function is f of z is e to the iz over z. Z is x plus I y. Y is greater than or equal to 0. The absolute value of z equals r. And we talked about how last time we could try to say, well, the integral over the semicircle of radius epsilon, of f of z dz is going to be less than or equal to the maximum of f of z times the length of the curve. And the length of the curve is just pi r. Right? But what's the maximum value of my function? Well, I'm on the semicircle. I have e to the I z over z. What value of z is going to give us the largest value? R. And so that would just be 1 over r times pi r is pi. It's not going to 0. So if we try to be crude, we have a bad result. But what we're doing here is we're being stupid. We have e to the iz, that's e to the ix, e to the minus y, with y greater than 0. This has decay, right? So we really don't expect this to be contributing much. So the problem is we are using the largest value of the function everywhere. Why would we use it everywhere? Most of the time there's going to be some decay. And so what I want to do is I want to talk about the thought process. And we may not get to integrating over the small semicircle of radius epsilon. That's the standard integral we've done before. I'll leave that one to you. I want to keep talking about the bad piece. So again, we have minus r to r. We have our semicircle like this. And what I'm going to do now, is I'm going to just zoom in a little bit. So here's 0, here's r, here's my blue curve, and I'm going to choose some angle or some critical value of y, either way. Okay? And so once I go to this critical angle from this point onward, from here on up, f of z is going to be less than or equal to e to the minus y theta over the absolute value of r. So as long as y theta has some growth with r, we're going to be fine. Okay. As long as it is going to infinity at any rate, that's going to be enough to win because we just barely missed. And then what we want to do is we want to show that the integral from, let's say, let's call this theta sub r. The integral theta goes from theta sub r to pi minus theta sub r f of z dz, plus the integral theta goes from 0 to theta sub r f of z dz, plus the integral theta goes from pi minus theta r to pi of f of z dz. That's going to be our integral over the semicircle, these three pieces. On this piece, this is going to be in absolute value. It's going to be less than or equal to, oops. It's going to be less than or equal to e to the minus y theta sub r over r. And how long is my arc? Yes. R times theta. And what is the theta here? Not theta r. I'm integrating from theta r to pi minus theta r. Pi. It's actually pi minus 2 theta r. Who cares? Theta r is going to be really small, so I can bound this times pi. So as long as y to the theta r is going to infinity, I'm going to get that extra exponential factor. Now over here, if I want to bound this is going to be less than or equal to, what's the largest f of z could be? Again, 1 over r. So let's do 1 over r times theta r. And similarly over here, this will be less than or equal to 1 over r times theta r. So now we see that as long as theta of r is growing slower than r, these are okay. So we win if theta r over r goes to 0. And here we win if y theta r goes to infinity. So all we have to do is choose a theta so that y of theta is going to infinity and the theta r is going to 0 when you divide by r. Okay, so I will let you put in the rest of the algebra. So you need to find theta r such that 1, y theta r goes to infinity, and 2, theta r over r goes to 0. And so if you're trying to think about what's going on, so here's my minus r, so plus r. Here's my theta r, here's my y. So can somebody tell me what y theta r equals? So sine theta r, almost. R sine theta r. And if theta r is small, what is r sine theta r approximately? It's approximately r theta r. And you can actually show that this will be greater than or equal to r theta r over 2. It's going to be at least that big. So if we take theta r, we want it to be something small. What would be a good choice to take? I'm sorry? So if you take 1 over r squared for theta r, if you then multiply by r, you get 1 over r, and y is no longer going to 0. So you made your angle too small. We wanted the y to go to infinity because we need that first term, e to the negative y theta r, to be going to 0. So we need y sub theta to have some growth. So if you take theta of r to be 1 over r squared, it's too small. Square root of r would be fine. So if we do square root of fine, so more generally, do r to the delta. Delta in, say, 0, 1 should work. Or you could do maybe theta r is 1 over log r. And so I like to have free parameters to play with as to how far can you push things. Okay. And so this is enough to show that the integral over the top of the semicircle is not going to be that bad at all. We broke it up into 3 pieces, and we said, well, look, if we try to use the same bound everywhere, it's not going to work. So we have to be a little bit more careful. And now all that's left, and I'll leave that to you, is to just figure out what to do over that small circle. All right. So, I hope this helps to go through these calculations, show all the details to show the thought process of how you attack problems like this. Nowadays, you just punch it into Mathematica, and Mathematica has all of this programmed in automatically. But in case there's an electromagnetic pulse that's detonated and all the computers go down, you at least now know something to do.